right. So basically, I was contacted by someone from CanBIM. His name's Daniel. He works at a GC, a general contractor, PCL, in fact. And he asked me to talk about what he thought was worth changing in our BIM environment. Are you seeing my screen all right, Curtis and Carl and everyone else? Are we good?
Yeah, you're good.
All right. So he basically said, like, what do we do? How do we propose change? How do we work more efficiently? Like, how do we make this BIM stuff work a bit better? So we got into a pretty long debate, and we sort of circled around one specific example, which I'm going to get into. But the point is, the biggest point that everyone probably knows or should know, or at least if they don't, it should be reinforced, is that the traditional process has changes in RFIs and issues and modeling, and everything that involves BIM happens, in my opinion, way too late. This is the McClemy curve out of 2004, and it's a real easy illustration of when you want to do things. So you want to pull ideas and concepts and communication, referring back to what Tom Strong was saying earlier at the intro speech. Like, how do we communicate more effectively? Well, we should be doing stuff earlier. That helps with communication. And if we can make some tools around that and take a bit of time to figure out where our waste is. So with that in mind, this is the first part, which is probably the biggest part of this presentation, is the day that the Calgary CanBIM audience, that's you guys, saved $1 million with a toilet. My hope is that this concept rings, it makes sense, A, and then B, it can sort of spread a little bit, because I think we've got something here. So I work for Modern Niagara. Modern Niagara is a mechanical contractor. We've got offices in most major cities not most major cities, in Toronto, Ottawa, Calgary, Edmonton, and Vancouver. And we do a number of different institutional, commercial, light industrial projects across Canada. So we know toilets. That's what we install day in and day out. My hope is that we can teach you about toilets. So this will blow your mind. That right there is a wall-mounted toilet. You can see it's wall-mounted because it's not on the floor. This here is a floor-mounted toilet. You can see it's a floor-mounted toilet because it's on the floor. What I've seen in 20 years or 15 years of being in this industry is that I have not seen many commercial floor-mounted toilets. Most commercial, institutional, hospitals, data centers, office towers, they always use wall-mounted toilets because it's easier to clean underneath, and it allows a little bit more flexibility in the construction process. A floor-mounted toilet has to be perfect. The hole that goes through the floor has to be perfect, and that means the wall has to be perfect after the fact. It's too perfect a question. That's why there's usually wall-mounted toilets. I've probably seen 5 total in my career for floor-mounted, maybe 20. So what you may not know about is what attaches the toilet to the wall. There's this thing behind it called a carrier. It's a structural piece that does a bunch of stuff. And it creates a solid attachment from the wall to the concrete below, because that's the strongest thing that we got attached to. So it's implementing this solid attachment. It's allowing for slope drainage, because I'm going to get to that later, but I'm going to bring it up now. And then it also allows for the flexibility of the wall thickness, because sometimes walls have different thicknesses depending on if someone has some fancy tile or paint or whatever, or wood or whatever on the wall. It also allows for deviations in concrete. I'm not sure if this is evident, but concrete sometimes has little bows in it, depending on where it is between the columns. It also, tile thicknesses can sometimes be adjusted mid-project. And then there's also mistakes. So the carrier fixes a lot of issues as listed above. This is what a carrier looks like. This carrier right here is for bariatric patients in hospitals. It's very, very strong. It can hold 1,000 pounds. This is a more normal vertical carrier. a lot like that floor-mounted toilet, it involves a really high level of commitment. Here we've got the horizontal carrier, which I'm going to refer to later. The waste comes through the back into the toilet, and then it goes off this way. Fun stuff and exciting stuff, I realize, but I'm getting somewhere with this. So here's the carriers being placed on sites. So previously I was saying that you need to allow for slope drainage. If you can see here, the pipes are sloped ever so slightly from one end to the other so that there's a drainage fall. You can see it really pronounced here. It's going to this direction to the left. So here's a little higher and here's lower, and that's what all these bolts are achieving here. You're allowing the slope to exist and still have the toilets at the same level, because if you looked at them and they were all different heights, that would be weird. So it makes the architect and the client and the cleaning and everyone else happy, because it looks the same, but behind the wall, everything's changing a bit. So long story short, in my career, and I've done some phone calls around modern Niagara, like to a lot of different project managers, we've only ever seen in the vast majority of projects we've done, two kinds of carriers. There's a Watts carrier, which is on the left, and a Zern carrier on the right. And they're both horizontal carriers, as mentioned before. Vertical carriers are a little bit too precise, so people don't like using them. These things are the only two things that we use. There's another carrier called Wade. We don't, in our company, we haven't seen anyone actually use Wade carriers. So it's always Watts and Zern. The reason I'm bringing this up is it actually takes our constraints and the flexibility that's sitting in the consultant side from, unfathomable or really large. And if you actually think about it, there's two choices for almost every carrier installed in Canada. That's a pretty big note to take or put into one's mind. So there we are. Now, one of my mentors was a foreman in modern Niagara. His name's Lee Mehta. He's probably one of the smartest people I've ever met. And he had a rule. I went and asked him when I was like 24 or something like that. I said, what should someone do if they want to do a good job? Like, what's the secret, from someone who's like 60 years old and has been through and seen many of the projects across Canada? His quote was, "The best projects are sleeved well and the worst are not." So I'm not sure if you guys know what sleeves are, but I'm going to underline this. Again, a lot of what I'm saying here may be realized by, I'm hoping there's some consultants on the room. I asked a question in the Q&A, Curtis. I don't know if anyone's answered it. Have we got any consultants or owners in the audience? Curtis, you there?
We haven't got any answers yet.
Yeah, right here.
Did anyone answer that? I can't see that.
We've got nothing on the Q&A yet.
Yeah, we got
okay. All right, so I'll move through this. So a sleeve is literally a commitment cast in stone. I'm showing pictures of sleeves here. If you look on the floor, I don't know if can you guys see my mouse okay?
Yeah.
So here you can see all of these sleeves. Basically, they're tubes that are placed before the concrete is poured. They're a very, very high commitment item, and they cost a lot to implement well, and they cost even more to get wrong. So I'm going to go into that a little bit later. So what is a sleeve? A sleeve is a hole through concrete, but it's a commitment. It's a commitment cast in stone. So here we've got a carrier here and a sleeve on there's a horizontal carrier that we've talked about earlier, and then there's a sleeve through the concrete. These are sink carriers, and here's a close-up of it. And we use a Trimble survey laser rangefinders to position our carriers before anything else is placed in the building. This is a very accurate process. We do it well. Historically, we used to have a failure rate of around 10% or 6 to 10% on our sleeves. Now, on our most recent projects, we're actually getting almost below 1%, if not 0.5%, which is pretty amazing. That difference has happened in the last 4 years, that level of accuracy, which is pretty great. So the sleeve here that needs to happen is defined by the sink. In this case, here it's defined by that toilet. If you look here, the sleeve I'm going to get to this later, the sleeve is driven by the place of the toilet, not the other way around. And there has to be a lot of precision here because you haven't got a lot of room for extra pipes or whatnot. You can't fit any extra bends and all that. You have to do this well. And if you don't, you're into a pile of trouble, which I'm going to get to shortly. Underneath the concrete, before the concrete's poured, this is what we typically see. I think I would assume that as someone who hasn't seen this kind of picture before, the amount of content that's in a slab that's buried in the concrete around the sleeves is phenomenal. All of that gray pipe that you see there is electrical conduit. If we were to cut one of those electrical conduits, it could cost tens of thousands of dollars to fix that issue. You can see all the red arrows, and they're pointing at sleeves that have to be put onto the deck before the rebar is put there, because it'd be almost impossible to move the rebar after the fact. The things on the right are wall sleeves for a Canadian Nuclear Safety Commission approved LINAC vault. And it shows, again, the level of detail and multi-trade coordination that has to happen with sleeves. Back to Lee's comment, a sleeve is a really big deal, and it's hard to get right. And if you get wrong, what happens if you miss one? Well, the answer is it's not good. So if you do miss one, you're going to have to do something like this, which is called coring. Coring is a nightmare. It's really, really bad. I'm sure most consultants and owners, if they've heard of this kind of thing, think, oh, the trades have to do a core. That's crappy for them, and it is. It's really bad for the trade. But I think I'm gonna try and make the case where it's not just bad for the trade; it's bad for everyone. So here's a story of a core. Step one, we think we've got a toilet figured out, and we mobilize our site laborer, site installer, and journeyman tradesman or apprentice tradesperson to go and install one of those carriers and the pipes and all that stuff around it. So the worker goes there and mobilizes to the location where there should be a sleeve. He's happy, he's good. Step two, the site worker finds no sleeve, but only after searching for it for a half hour because they hope that there's a sleeve. And now they're going around bashing on the concrete, trying to find if it's been slightly covered by a little bit of concrete. So they've wasted a half hour. Then they have to demobilize because what they did, all of that pipe that was on their shoulders, that's now not useful, and they have to go find another job. So they have to go back to the site trailer or their site foreman and figure out what's going on, but only after they've talked to the site lead and the site lead has come and looked at the problem and realized that the problem exists and what the hell they were going to have to do about this. So the point of this is we're now out $135,000 or $135 for one sleeve on our site labor. Now the office staff is now engaged. So the project coordinators, the BIM staff, the project managers, and whatnot, and the trade office, they are now engaged with a problem. Someone has to go capture photos. Someone has to find alternate routing, looking around on the site and possibly in the BIM model. Coring and X-ray has to perform. The only person who's happy in this one is the coring supplier or installer. It's usually subtraded out because it involves a lot of expertise, such as using X-rays, seismic or ultrasonic scanning. It's expensive. Each sleeve is going to charge $200 roughly for finding what's below. And if you remember all the concrete and conduit and the rebar and all that stuff, that's going to cost $200 each time because you have to scan everything. And if it's a really thick piece of concrete, you're going to have to scan it more than once to find a little tiny spot that will work, and you can drill through the concrete. The BIM team may have to redraw the systems for an alternate route depending on what the BIM specifications of the project are. So now we're at what we were 130. Oh, sorry, and the PMs have to write an RFI to officially submit to the project team, which is the GC and the consultants. So now we're at $850 minus out of the trade contract. They typically don't get paid for it. This is all ripped out of profit, which is not good. Again, if you refer to my earlier sentences on previous projects, we've had 1,000 cores, which was actually deemed to be pretty good on a major hospital. On our recent hospital that we're working on, we're below 200 at this current stage. But there's a hitch, which I'll get to later. So now the RFI gets sent out. Misery loves company. The GC has to go and read through an RFI about a core, which is going to be complicated. The consultants have to go and review that same RFI. They have to figure out where it is in the building, go through all of their drawings, figure out what they tried to do, and then look at the problem and see what they think of the solution, or come up with a solution of their own. So now everyone's starting to hurt. And across the whole project, the consultants have spent roughly $715. The trade is now at $800, and the contractor's at $100 because they've had to manage the communication flow at a minimum. The RFI response comes back from the consultants. The GC has to vet it again through their tracking system, as Carl was mentioning. They have to send it to all parties because all parties have to know about this, not just the mechanical. Maybe the electrician has to know about it because the proposed sleeve might affect them. Or maybe the architectural or the furniture person needs to see it because it might affect where a piece of furniture gets placed. Everyone gets pulled down into this mire. All parties have to read it. And then the trade reviews the approved or instruction from the consultant. And then once they've reviewed it, then they have to implement the core, which is actually fairly cheap. It's just all this bureaucracy behind it. So now we're at $715 for the consultants. Trades are now at around $1,000 or $1,100, and the contractors spend $200 on administration. Then the site worker has to remobilize, which they already did, so we've lost an hour here, and they have to install a workaround which has a bunch of pipes going to another sleeve as opposed to the intelligent routing. It has to be a compromise, wasted pipe, lesser overall product, bad news. So now we're at $1,200 spent by the trade, $700 by the consultant, and $200 by the contractor. We have a reasonable project cost, which the owner bears because all of those prices are built into our historic trends as companies. So $2,000 per core minimum. The consultants have to spend money and deal with contract management, all of which is avoidable and slows them down and lets them not get to another project, which would be more fun, more advanced. And everyone likes drawing a new project. They don't like fighting with cores. It's soul sucking. But wait, there's more. We actually have seen cores that were required that have cost modern Niagara $25,000 each. We're working on 2 cores in the project that I'm currently working on. 2 cores that are costing $50,000. Why? Well, as buildings get more and more efficient, and engineering gets more and more efficient, and owners demand more and more cost optimization, rebar becomes engineered to a very finite degree. There's not a lot of extra strength left in the building. If we hit a core because a scan was done improperly or a mistake was made on site, and those things happen, and you cut 2 things just like this, then you have to jackhammer this hole, which was done by our forces, above and overhead from the floor below. Then they have to get an engineer to figure out how to weld all these bars together in a form that's as strong as the original shape of the rebar. That's what you're looking here. You're looking at rebar that are welds that are like 5 to 8 inches long. This takes like 4 hours to build. It's a position weld. It's slow. It's horrible. It's bad. So that's $2,000 is the minimum. $25,000 is the maximum. Somewhere in between is the average cost to the building owner, the consultant team, and the entire project. We're not just talking time or cost, we're also talking time and delayed, extra labor power that's needed, people doing boring work, which is no fun. We can avoid this as an industry, and we should. So the traditional consultant approach, these are consultant drawings that were drawn in the last 4 years. As you can see here, there is no chase that allows for the room for the carrier behind the toilet. That's a big mistake because what's been drawn is impossible. It does not work. You can also see that where the carrier is and where the sleeves are not accounted for. So we have here's our trends that we have witnessed in the last, I'm going to say 10 years. Carriers are never modeled with one exception on one project, meaning one project was the exception. Chases are rarely included as per the drawing on the right. Sleeve drops, which are the sleeves themselves, are never accurately accounted for nor are they accurately dimensioned or drawn or reviewed by the structural engineer, which means that any sleeve that is committed probably has to change and go back through the engineering, so the structural engineer's approval to make sure the building doesn't fall down because there's not holes everywhere or in the wrong spot. Why? Well, the reason that these problems exist and these trends exist is it's challenging to draw sleeves and it's challenging to understand. It's not challenging to do, it's challenging to understand, and it's typically not thought of in the consultant's scope. There is no tool. There's no easy way out. It's poorly understood. The consultants don't understand every fitting that happens behind a carrier. Most of them haven't gone to the level of depth that we've already gone through in this presentation. The trades will catch it. So don't worry about it. The trades will catch it. Well, yeah, we will, at a cost to everyone of $2,000 per toilet or a core, or like there is a cost that could be avoided. So if they do model it, they model just the carrier and then rough piping. So just throw down a carrier like that we see in Revit. Rarely are carriers modeled accurate at all. And generally, I have not seen a carrier modeled accurately except for one project. This is another consultant drawing by a different consultant, and it shows the diagrammatic rough position of the carriers and the sleeves. So this sleeve right here that's going down here and here is impossible by the geometry defined by the carrier. It's too close, which means it's hitting the wall, because the contractor is going to have to move it to the north. It's going to hit the wall. It's going to affect the wall, and you may have to even move the wall. That's a big change. That affects every single person on the project, and it slows every single person down. So this is a typical RFI that we have to figure out. And what we do is we go through and audit at the beginning of a project, or as fast as we can. If it's too big a project, we just do it in front of the project critical path. We go through and we make drawings like this. So we say that sanitary chase is not wide enough for water closet carriers. Please approve of our proposed location for walls, or find an alternate. This takes us tons of time. The cost of the project are 10 to hundreds of hours of BIM work, depending on the size of the project, to go through and make these red lines on the consultant drawing. Then the architect has to go and check and make changes to their design at roughly 1 to 3 hours per toilet. And it might not take the architect 1 or 3 hours to move the wall, but you have to remember their contract administrator has to read through the RFI. They have to bring up the RFI, load the model, and then get their head into the game, and then make the change that is proposed if it's deemed acceptable. If not, then they have to spend 2 hours finding out something else. It's a huge waste of time. One of these RFIs can take them a lot of time. Structural consultant is going to have to then check, once the architect's approved, all of the toilets to make sure that the holes are okay. The general contractor has to manage all of the walls that have been moved around. Maybe they have to retender the walls, or they have to allow for costs which are now outside of contract. Everyone knows that outside of contract changes cost more, and and costs balloon to the end owner. Bad news. This is an example of the level of changes that have to go in just because of water closet carriers on one tiny drawing. The project that this pertained to, we had like 10 drawings that were updated, all for the RFI search on the water closet carrier issue that we've been outlining thus far. So the cost of Chase RFI in a small size project, I figure, is $4,000 to the owner, or to everyone, for about 10 toilets. I'm gonna get to this later, and it could be as much for a mid-sized project as $20,000. I'm saying like around 30 to 50 toilets. For a hospital, which Modern Niagara has been known to build, we're into the hundreds of thousands of dollars at least to the trade group, as well as the consultant model. The approximate wasted time, to make this a little bit more concise, is $400 a toilet roughly for a small project, and $500 a toilet for a mid project. If you think of the slowdown of finding out the toilets that are wrong, and the sleeves that are wrong, and the sleeves that need to be investigated, for that thing to go from identification to rectification, or to rectify the problem, we're at 25 days for a small project and 60 days for large projects. That's a lot of risk. That's a lot of slowdowns. That's a lot of waste. That's bad news. And it's a lot of money per toilet. So now back to the carrier and sleeves, because now we're going to link them together. It may not be evident, but the carrier defines the sleeve. So the center line of the toilet, which is defined by the architect, because they need to know where the toilet is because of building code, to the end of the barrel is the barrel distance. Then you've got the distance from the end of the barrel to the sleeve itself. And you need to leave room for a 90, maybe a 6-inch stack, because you could have a 4-inch stack or a 6-inch stack, and then a little tiny piece of pipe in between that allows for flexibility if any one of these things is off. If you're short 1 inch and you don't have 1-inch tolerance, then you've made a mess. So you need to leave a tolerance piece. But this means that the distance from the green line to the far yellow line is finite. Let's recap. Coring is really bad. No one wants to do coring. It's either $2,000 to $25,000 per toilet. It increases the cost for all parties, slows down the project, increases project risk, and the missed sleeves lower the quality of the end product because now you're starting to add bulkheads. The thing looks like garbage, and it's not a good building. The consultants end up having to deal with corrective actions anyway, because they have to redraw it if it's a core or if it's caught before a core has been missed or a sleeve has been missed. It's still, the consultants have to deal with it. Missed sleeves or cores must be dealt with during contract administration. The affected architectural content may be put at risk. It needs to be analyzed and it needs to be dealt with. And the carrier defines a sleeve. So what we've done is we've created a family that provides center line markers. It also includes for code distance to wall locators. These little things here are a visual tolerance so that our modelers can check whether or not a wall is outside of code and the toilet has to move, because sometimes that happens. Also, it's got a target zone for where a sleeve should go, and it will always work. A carrier with a an attached guide sleeve, which is as shown here, so you can place the sleeve on the structural drawings, is a way better option. The carrier defines the sleeve. So now, if we could give this RFA, or family, Revit family, to the consultants would, without knowing the ins and the outs of everything, they would be able to place their sleeve targets. Then the following becomes self-explanatory. Trade knowledge is now not required by the architect or the mechanical engineer. Immediately, the architect can see if their chases are the wrong size by using the sleeves, and they can also identify where their cores should be. What if there's a column cap or a beam below? The structural engineer can say, I'm not letting you put a sleeve there. All of that stuff that ends up hitting them in duress once the project's been awarded at great cost can be completely avoided if the architect and mechanical engineer use the RFA sleeve. In the meeting that we've got going on right now, Carl has uploaded a document that has a hyperlink to this, this RFA sleeve here. This would help the industry if we just use these things. We have to use them anyway. It's already built into the process. But if the consultant used it, as they did on the most recent project that we're working on, which is a fairly large hospital in Calgary, what we did was we gave this carrier to the consultant, and all of these discussions and all of these RFIs dissolved. They were dealt with at the design level, not at the trade level. The entire project, I figure, saved at least $500,000, if not $2 million. If you think about the amazing impact of providing good trade quality detail to the consultants. We're at 7:46, so time is going pretty well. I'm going to move to the next thing. So at a minimum, so coring is really bad. To recap, consultants end up having to deal with it anyway. At a minimum of $400 per toilet, all we need to do is place 2,500 water closets based on this RFA family right here. At the easiest case, and at the worst case, probably around $1,000, we can save $1 million of profit in Canadian CAN-BIM methodology by implementing this very easy process right now. Or better said, we're wasting $1 million every time our industry does not fix this very intricate but simple problem that we are doing to ourselves. We should be saving money. We should be not accepting traditional processes that allow these changes to go on and on and on and on and on throughout our industry. It's an easy way to save a pile of money and work more effectively. Think of all of those RFIs that don't have to happen. Think of all of those people that can now work remotely, as Tom was saying. Think of the communication that now happens without even speaking. It's phenomenal. This kind of thing and the thought behind it is what I believe the subtrades and the consultants and the owners should be looking at with real eyes, figuring out how to implement for system-wide efficiency. Now, here's another example to the same exact effect, pretty clearly said. So generic fittings come in Revit, and we see these all the time. This is a consultant model of a very recent project that we're working on. That fitting is impossible. No one makes a 90-degree fitting that small, which means you're making a geometric falsehood. Using pipe fittings that are impossible to install drives the consultant away from the realistic install. It starves the consultant modeling group from the ability to model reality. If they model a lie, then they never can comprehend, or they have difficulty comprehend just by the system that they're using, what is actually real and what is installable. Back-to-back fittings are now false. This is a huge effect because it throws off how pipes are placed in a building. What looks fine in a consultant model can end up being impossible simply because the fittings are a lie. Pipes are allowed to be put too close together, and all geometric agreements are now compromised. Again, we've made a geometric falsehood. It is likely that the use of generic Revit fittings is one of the major reasons that consultants have such a hard time making realistic, installable, and coordinated models. Unless the consultant modeler understands how big a fitting is in their head, and then they put it into the model, what they'll do is they'll shortchange all of the room that it actually takes to do things. This is a welded 90. Welded 90s are the biggest 90s. If you make a system that can fit a welded 90, you've made a system that can fit any 90. Copper, Vitalic, mechanical joints, screwed fittings. The welded 90 is the biggest. These are very easy to get and available with any internet search. And the rule is that the diameter, the nominal diameter, which is listed in this chart, compared to the dimension A, is 1.5. So if you have a 2-inch fitting, it's roughly 75 mils on A, exactly. If you have a 4-inch fitting, it's 150. That pattern exists. It is not shown, and the libraries are wrong in consultant models. If the consultant models just change the libraries to welded 90s, then every geometric commitment that they make would now work. You can see from our model that the 90s are much bigger than this one, like meaning the sweep. The 90 sweep is bigger, and we know where to put the T compared to the 90. Whereas a consultant model might put the T too close, and then they hit a wall on the far side because everything has to move forward. That's the kind of subtle impact that a generic fitting makes. A generic fitting should be illegal. These should be illegal. What should happen is a consultant just changes their libraries to welded 90s, and now you've got solutions that work everywhere. Your own modeling group starts finding out what's wrong with the building rather than not being able to determine it because the fittings sort of lie. We can implement this now with any consultant, and it's a good metric it's a good thing to reach for our industry. If we saw this, then the subtrades would be able to create their models faster because they wouldn't be making as many corrective actions to the building at large. Things would just sort of work. So the consultants have to draw the fittings anyway. At no cost, the consultants can uncover much more project risk earlier because now they can see the reality of what the fittings look like, where they don't have to wait for the trades. There will be a natural education of the consultant modeling group that is currently trapped in the trade group. What I mean by that is because they don't know what a real fitting looks like, they don't think like an installer. By using a real fitting, they'll start naturally thinking like an installer, and all of the problems will be wiped away at the earliest stages of the design. Think back to the McClelney curve. You're taking what would be a bad problem at the later stages of a project and pulling them towards the earlier stages and saving a lot of money and allow the project to be built faster with less risk. Everyone wins, and everyone gets a lot more profit because there's not as much contract administrative costs dealing with RFIs and mistakes that have been made and that are inherent in the design. VAVs are similar. So here you've got a VAV by the consultant side, and here's our VAV. And I'm even going to bring this up. Ours aren't perfect. We have complaints with our own VAVs because we constantly see what needs to be improved upon. Our VAVs show the coils clearly. We also have got a measurement from the coil to the pipe because there needs to be a coil pack between the two of them. There is no such detail in these consultant VAVs. Because there's no such detail, things like this, the two VAVs get put too close together. That's bad. Also, without showing the access hatches, you could put an access hatch in a wall, which would mean that the whole duct system has to be redesigned, or maybe the wall has to move. All of that could be identified easily at no extra cost at the design stage if the family was drawn correctly. Said again, we should be drawing the access hatches. We should be drawing the coil connections. We should be drawing something like the coil packs. It doesn't have to be precise. The coil packs are the balancing valves and all the valves that go in front of a VAV. And the minimum upstream length. There's a VAV requirement on the airflow going through the VAV. If we were to do these things, these tiny little things well, which again is just taking 10 to 40 hours to do one family that can be used on all projects going forward, then the consultant would have a much stronger model that would mean that there's less repair to be done by the trades or the site installers, which is inevitably what's been happening in the past for our industry. Attenuators may not be an issue, but they can be if it's fire rated. That's a little asterisk if someone wants to get advanced. Some ideas for fixing the problem are create a generic worst case VAV from preferred trades. Why doesn't, if you're a consultant, phone your top 3 or top 2 trades, have a meeting, and let's make a community-based communal family that implements all of the things listed here. Call your trades, find out what they prefer for VAVs, and figure out if they can help you get rid of a lot of the issues that are just buried into the design due to an insufficient detailed VAV. The GC could also demand, I hope there's some GCs in here, if the GC demanded on a project schedule the VAV procurement within the first 6 weeks on a per item price, because a lot of these things go on all value, like they try to find the precise quantity and then they get a locked in price. Why not do a per item price with approximate volumes? This would work on design build, IPD, and design assist, and it would allow the consultants to have the perfect either carrier or VAV or whatnot. The GC should pull the mechanical trade forward in the procurement planning to figure out how to get their content and their geometry in the models as fast as possible. This stuff leads to hundreds of thousands of dollars of waste that could otherwise be avoided because someone's trying to save $30,000 on procurement. It doesn't make sense. So to recap the learning goals for this presentation, identify your geometric project risks. The devil's in the details, but it's not hard to implement. Stop ignoring the sleeves and the carriers or similar items on the project. Start with the carriers. Trust me, it's the biggest thing, and it will make a huge difference on any project. 2, make a list of the low-hanging fruit that consultants can implement on behalf of the subtrades. Talk to your subtrades and start collaborating. Start figuring out how to get that one family that can be sent to the architect, and it destroys hundreds of RFIs on your project. Vet your families, but seriously this time. Don't just take generic as good enough. It never was, and it isn't. Lastly, bigger is better. Consultants need to start thinking about adding 10 to 20% of the dimensional size for equipment. So if they think it's 100 mils, make it 120 mils. If you don't know what the equipment is, if you make it bigger, then the corrective actions are always easy to implement. We are seeing a trend where equipment is actually being modeled smaller than reality, and this buries the risk and drives it to the owner, the trades, the consultants, and GCs. I think it's the responsibility of the owner, the consultants, and the GCs to not allow these bad trends to carry on. They've gone too far, and it ends up costing the owner money and all of us money in lost profits. Hopefully, we've illustrated the importance of this stuff. So now we're into the QA session.
Hey, Chris, thanks so much for that great session. Obviously, all of the audience was very engaged because we didn't get very many questions. We did have one that popped up in the Q&A that I'll ask you. How do we get this to change? And I think you addressed that with your recap, some of those great suggestions. But specifically, the question asked about, do you think this is something that we maybe should address with Autodesk to see if perhaps they could improve what they have?
Yes,
there?
That's a great idea. I think that Autodesk is really, it's a bad move with their generic fittings. It's a really bad move. They should wipe the old ones and replace them with big fittings rather than small fittings. It'll annoy a lot of people, but that's the point. Because when you make something too convenient, it's like hiding something under the rug. You might as well annoy the designer, and so that they see how hard and difficult the design is that they're fighting with. That's how to make a better collective and community that's modeling this stuff, and our designs get better.